Yeah, okay. I mean, I'll just start the class. So if someone can able to join, I mean, they will join in between. So what I'll do, I mean, anyhow, the session is recorded. First, let me open the stat model. My voice is clear, right?
Yes, sir.
Okay, fantastic. Okay. So there are two models which we did, I mean, like, in the class, I mean. So I'll just go with the office building. I'll start with the base plate connections. So what I'm going to do, in order to extract the reactions, I mean, so I'll just switch on the node number, which is shift n. So shift n, I mean, it shows all the node number, even including column to beam connections as well. But whereas I'm going to do the base plate connections, so either I can take it like, the exterior column 1, 2, 3, 4, 1, 2, 3, 4, or the internal column actually, which shows like, 6, 7, 10 actually. Just try to understand the concept, I mean, how we are going to extract the forces. In order to understand like, the positive, negative signs and which direction we do have shear. Shear, you do have two directions. One is vertical shear, another one is horizontal shear. The another critical one is moment. I always used to say, I mean, whichever the forces which has like, highest moment, try to extract the forces first. Then if you think, no, I need to extract the direct tension as well, which is axial, I mean, then extract it. So it doesn't mean that actually you need to extract only one forces. Like, you can extract the forces from the multiple combinations. I mean, so might be like, there are one combination where the moment is higher. I mean, okay, there is another combination, maybe direct tension is higher. But what I'm trying to say, the moment which will be like, give indirect tension is much more higher than the direct tension. Okay. Let's see. I mean, so I'll just, point out the, what do you call, node number one actually here for an easy reference. In order to confuse here, so I'll take it here, node number one. Okay. To extract the node number one, you remember, I mean, I shown this step during the classes, which is result setup. The result setup, what happened? What I'm going to like, refine the load combination. If I forget before going into the post processing, then anytime actually you can customize the, what do you call, load combination and the, what do you call, the support reactions where exactly you wanted to extract. So that's how which we are going to do it now. Okay. So what I'm going to do, I need to extract the support reaction number one. So I'll go to the result setup, the ranges, and the ranges I'll just mention one. Okay, there won't be any kind of beam number and loads. And remember, I mean, whenever you are going to do the connections, you have to do the connection design only by using the ultimate cases, not by using the service combinations. Okay, so I took all the ultimate combination the right hand side. Actually, previously it was like this. So what I'm going to do, so I'm only selecting what you call the factored combinations. Okay, then going with mode, post processing, node, reactions, summary. Okay. So this is the reaction summary for the node one. Okay. Maybe like, some of them, they have some kind of confusion. So why, how come it shows only one? I mean, okay. What I'm going to do, just for a clarity, what is this number? Is 13. So I'll change from 1 to 13. The moment when I change, whatsoever it shows the node number 1, it gets changed from 1 to 13. Okay, see, can you see here? So what I'm trying to say, you can customize the extracting the support reaction, extracting the beam forces at any time by using this command, which is called result setup. Okay, so let me just go for it. I mean, okay, yeah, let me go for the same numbers, which is 1. Okay, so mode, post processing, node, reactions, summary. Okay. Okay. So this is the, what do you call, yeah, here. So I'll just copy this. Yeah. So this is the support reaction with respect to what? With respect to factored combination. Now try to understand. Can you see here? There is a factored load with due to dead load. So when the dead load which comes, I mean, definitely the forces with respect to the axial, which will be only compression, right? There won't be any kind of doubt in this. So dead load, it shows 5.48, which is positive in the sense it is compression. I mean, the axial force, right? The axial force which is acting along the member. I mean, okay, along the member. If I'm talking about the columns, the axial is with respect to the axis is Fy. If I'm talking about the beam, the axial which is Fx actually in this beam. If you're talking about this beam, the axial is Fz actually. So with respect to the directions, with respect to where exactly you're going to design the connection, the axial is get changed. Okay. So I'll go back to the Excel again. Okay, so this is my, either it is going to define the compression and tension with respect to the signs. Okay, then let me extract the factored combination as well. So what I'm getting 19.53. The moment is higher, right? Okay, so I can say this one is going to give me the maximum momentum. Okay, fantastic. When you go here, it's all compression. Can you see here? It's all compression. There won't be any kind of tension, direct tension, what I'm trying to say. But you do have a huge tension by overturning moment. Okay. So the actual compression is 11.5. Okay. Let me write it. So which is, I'll just, what do you call? So which is 12 kilonewton. Okay. Then Fx 16, Fz minus 17, max minus 19, mz is what? Minus 20. Okay, minus 20. And going back to idea statica. So when you open the idea statica, it looks like this. Okay, and in this there is an option called the connections. Takes some time. I mean, you'll open the idea statica. Oh, so going with the base plate connections. So if you just scroll down here, this is what actually is going to describe the connection type. So I'm getting base plate connection here. Okay, and this is what it shows the geometry, whether you do have square or rectangular column. However, you can change the section sizes even by choosing the first one as well. Okay, and if you go for the third sections, I mean, it defining where you do have a stiffener plate, where it's a pinned connection. Can you see here the bolt which is inside the section sizes? The first one is actually which is a fixed connection, because the bolt is away from the section. Okay, and the steel grade is S275, and bolt M20, which we can change it. I mean, even while going inside, I mean, this is all just a template. I mean, so what I'm trying to say, we can just choose a template, and whatever the section sizes and bolt diameters and base plate dimension, everything you can go and change, even including the code as well. Okay, so let's go for create project. Okay, yeah, the screen it shows
Excuse
like
me,
this.
1 second, please.
Yeah, 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 yeah.
My idea statica this time it again started showing like sign in and all those stuff like the
Yeah,
first day.
yeah, yeah.
Yesterday it was working.
Yeah, this is what the problem, because whenever you are connecting to the internet, I mean, the patch file
Uh-huh.
it get eaten up actually. Okay, so you don't
Oh,
need to
okay,
worry. I
okay,
mean, again, you need to uninstall. I mean, but the setup file and how to install the softwares, no, it has been given. So again, you need to install, because this is
yeah,
what the problem only for the Idea Statica alone. Idea Statica, whenever you try to connect to the internet, actually, because now they made it very strict. You know, so they were just,
okay,
closely monitoring not to use the pirated. I mean, such kind of things is going on only for idea static actually. Okay. So this is
okay,
where we even we ourselves be facing many problems. Even just now, you won't believe 15 minutes before I uninstall, I installed again actually. It shows the same sign in. It was working
okay,
since from
okay.
the morning. I mean.
Yeah, okay,
Okay. So now what is going to be happen? Let me see what is my column size. Okay. Just double click here. The column size is, go to property. So going back to the property, the section size is UC 203 46 kg per meter. So now going back to IDEA Statica, so I can change the column size. Yeah. So I'll show it again actually. So just go to the column here. When the moment when you click the column, the dialog box will get changed. So in this dialog box actually, there are two kind of section will be there. One is you can edit whatever it has been there, or you can create the section sizes. There is a plus mark will be there. The moment when you click the plus mark, there is like small dialog box will appear here. Either you can if you want, you can even create the built up sections. Okay, even if you want, like you can go with the standard section with respect to, like US, UK, Chinese, Dutch, whatsoever it is. So let me go for, like I section. So here, and the moment when you click, like favorite actually, it shows only, like limited sections. And again, there is an option called all. Then here you will see, like all kind of sections. Okay, so when you scroll down, I mean, you will see UC. Yeah, can you see here? Not UC Singapore, I mean, don't take it actually. It more or less similar, but take it directly UC, because in Singapore, what happened actually, there will be limited section only will available. But in direct use, actually, you will get a complete library of standard sections. Okay. So 203 46 kg per meter, 46 kg per meter, and just click OK. So, and ensure what is the grade. I mean, since we've been used from the beginning is S275, you don't need to change it. I mean, but if in case if you're going for higher grade actually, then you can just change the higher grade actually. Okay, higher grade, changing it to S275 or S355. But to be honest, I mean, only these two grades we are normally using quite often actually. Okay, so we are not using, like more than 355, but you've been using, like more than 355 actually when the loading is been, like bit higher, or when the structure is very complicated. In that case, actually, I cannot increase the section sizes only to pass out in terms of design. Then I will go for higher section, not in terms of deflection. You need to understand actually. Okay, then just I'll go with S275, because our design has been based on S275. I'm not going to change it. So S275, and I'm clicking OK, then OK, OK. So now what happened? The section sizes has been changed. Fantastic. I'll come one by one actually. I'm not going to be in very hurry, like to jumping from one to one actually. So once we fix the section sizes, I'll go to the base plate. Without changing the base plate dimension, don't jump into the bold dia, because it doesn't make sense. Huh? So you need to, like what we call, fix the base plate dimension first. How do you fix the base plate dimension? This we have discussed several times in the classes. But however, I wanted to show you. So here the section sizes is how much? 203, right? Actually, so from the face of the section to the center of the bolt, you need the clearance actually, because in order to use the wrench to tight the nut, I mean, minimum 30 to 35 millimeters. So let's consider 35 millimeters. Okay, sometimes we'll go for even 40 millimeter as well. Okay, let's consider in the worst case 40 millimeters. So 203, and both sides will have 40 plus 40, which is 283 millimeters. Okay, 283. Let me open the calculator. Okay, so which is 203. Yeah, so 203 plus 40 plus 40. Now coming back to the edge distance. Edge distance is how much? Minimum edge distance as per code is 1.25 times of diameter of the bolt. The minimum diameter of the bolt for the structural section, it should not be less than 12 millimeter dia, right? So if it is 1.25 times of 12 millimeter dia, which is 15 millimeter from the center of the bolt. Okay, so from the center of the bolt, 15, the sense actually 6 has already gone, because you are measuring, like 12 millimeter dia, isn't it actually? So 6 has gone. In that case, you will get only, like what do you call, 9 millimeters. That is not feasible. So what the code is trying to say, if we don't have, what do you call, maintain the edge distance, you should keep it. It is a mandate to go with minimum 1.25 times of diameter of the bolt actually. because sometimes we used to have this kind of problems while we are connecting to the slab thickness, like 150, 200. In that case, you will not have such kind of sufficient edge distance. Okay, but here most probably for the practicality they will go for 40 to 50 millimeter edge distance. So I'll go for 50 millimeter. So 50, 15 both sides will be 383. So it's odd number. I'll round up the number, which is 400 by 400 actually. So the base plate dimension going here, 40 by 40, which is 400 by 400, 400 by 400. Yeah. Okay. The reason why 98.5 I'm mentioning here. So 400 is my base plate dimension. Okay. Look at the dimension here. Yeah. Yeah. Look at the dimension here. So 400 minus 203, what I'm getting is 197 millimeters. So 197 actually. So the base plate, this dimension here, it shows like, from the face of the member to the edge of the base plate. Okay, from the face of the member to the edge of the base plate. This is what it shows top. Okay. So I'm getting like, 197 millimeters. Let me open the calculator for you for an easy reference. So 400 minus 203 divided by 2, which is 98.5. Okay. So 98.5, changing again. Okay. Even top also 98.5. Automatically it will get round up the figure. Can you see here? So it gets like, 400 by 400 actually. Okay. Yeah. Okay. Then going back to the what do you call? Yeah. Now going back to the what do you call bolt diameters, I mean. Okay. Coming back to the anchors here. So I'll just go for M16 diameter of the bolt, I mean. Okay. M16, I mean. Okay. The anchoring length. First of all, you need to understand for the compression force, you don't need any kind of like, what do you call bolt, right? Actually, because the bolt doesn't take the compression. You all know that. So when you're going to provide the bolt, it is only to cater to resist the tension force. Okay. So now you have this question actually. You don't have direct tension. Okay, and you do have only direct compression. So why we need to have this? This is what I told you. Like always you need to look at the momentum because this overturning moment is induce the tension force actually because the tension force which will be generated by the moment is very simple actually. Okay, the tension force equal to moment by lever arm. Lever arm is what? When it has been like having the moment. So what happened, like either this two bolt will be under compression, this two bolt will be tension. If you're talking about in cross, this two bolt will be compression, this two bolt will be tension. I'm trying to like explain you in order to understand. Okay, so what happened at any cost, actually, the distance between the bolt, which has been acting as a lever arm, right? Actually, which is resisting the forces. Okay. Then the moment divided by this distance, which you will get the indirect tension. Okay, so okay, since I do have like what do you call tension force on me, and don't go what do you call the embedment length not less than 200 millimeters. This is also it is there in the code AISC. Okay, 200 millimeters. But now our forces is huge. I mean, so I'm not going for 200 millimeters. Where I'm telling like if in case if you don't have like direct tension or indirect tension actually, if you do have only compression force, still I wanted to go for bolt in the sense only for the stability purpose. Okay, stability purpose, then you can go for 150 to 200 millimeters. Okay, but don't go for not less than that. Okay, but since I do have like tension force with respect to moment, so I'm going with here like say 400 millimeters of what do you call the anchoring embedment length. The one which you're talking about is embedment length, the embedment length below the base plate. Okay, now what is the anchoring type actually? The anchoring type, you do have three type actually. One is straight and washer plate with circular, washer plate with circular, washer plate with rectangular actually. Okay. Uh, and the other two anchors, we are not going to use it in practical because we will be using most often in straight anchor, or we will use like J bolt, or we will use it like what do you call the U type actually. Okay. So which is like I'm talking about J bolt in the sense actually which is U type. Okay. There's a L anchor will be like okay. So L and J, and as well as straight anchor. Okay. Now what happened actually? Then what is the difference between these three anchor? This L, say for an example, the one which you're talking about L. Let me just open the paint. The one which you're talking about, I'm talking about the straight, right? Okay. The one which I'm talking about L, the one which I'm talking about like J, right? Actually, okay. When you don't have place to, in order to maintain the sufficient embedment length, the embedment length which is going to be measured from here to here. Okay. So this is also part of embedment length. You need to understand. Okay. Here, the embedment length will be like here. Actually. Okay. From here to here, actually. Here to here. Okay. I'm jumping to the topic. I'm not going to confuse you. It is very similar to like development length. Okay, I'm not going to like correlate, but I'm just trying to make it in a very simple way. Okay, how many kind of development length is there? So you do have this kind of development length. Remember, actually, in a concrete beam or in columns or walls, when it has been like starting from the starter bar from the raft foundation, actually, you do have this is one kind of development length, and we do have like this is another kind of development length. Another is like what do you call, with the head actually, with the head actually. Okay, so there will be a head actually here, huh? There will be a head. This is special type actually. Okay, you're use they were using the normal rebar here, huh? Normal rebar actually, but in the edge actually they will make it as a head dummy. Okay, normal rebar they will make it as a head actually. Okay, so most widely we will be using only this and this actually. Okay, when you are using this, when I do have a beam here, okay, when you do have a beam here, then I will take the top bar here and here actually, right? Okay, here the development length when you're talking about actually from here to here, right? Here to here, this is the development length, but people are misunderstanding the concept actually. Okay, so you're 100% right, this is the development length, but the code which has been giving like two different kind of equation. When you want to go for a hook, then you need to use the different equation in order to calculate the development length. Okay, so when you want to use the straight bar actually, say for an example, my shear wall is huge, my shear wall is huge, my shear wall is huge, then I don't need to take it the what do you call top bar and to bend it. Say for an example, my shear wall is actually 2 meters. Imagine 2 meters. Okay. Then the top bar is say for an example 25 millimeter dia actually 25 millimeter dia. Maybe you're taking like talking about 50 times of 25 millimeter, right? This is what your the development length, right? In general, I'm talking about. Okay, in general, I mean. Okay, so 50 times of 25 millimeter dia, which is okay 1.25 meters, whereas your wall thickness wall length is 2 meters. In that case I don't need to take it till to the end, taking to the bend actually. Maybe if I satisfy like 50 times of diameters only like protruding inside the wall, that is more than enough. You're getting a point. This is what you need to understand here. Okay, again I don't want to confuse you. Coming back to the anchor bolt, okay, the development length will be measured from here to here and from here to here. If it is straight, then directly from straight to straight. Okay, so this is what the development length. Okay, so now we are going for straight actually, which is 400 millimeters. Even if you're using the straight, even if you're using the straight, yeah, make sure if you want to change it to L or J bolt, you can compensate this 400 millimeters by using like L and J bolt. It is not mandate that, I mean, since your design is being catered by using straight, and you're not supposed to use the L and J bolt. I mean, still you can use it. I mean, but only thing is, I mean, you need to comply this 400 millimeters at any cost. That's what you need to keep it in the mind. Okay. And coming back to this, what do you call the top layer? Yeah, the top layer and bottom layer is what? Okay. The bolt from the face of the column to the center of the bolt, it is the distance actually. Okay. Here it is little bit different in IDEA Statica because it doesn't show the edge distance. It shows from the face of the section sizes to the center of the bolt. Okay. So top and bottom will be 40 millimeters. And going with the weld, I mean, going with the weld. So I'll just go for like, the minimum authority requirements, the weld thickness, which is 5 millimeters. Since the forces is more, see, I'm not going to assume something which I'm not going to fix it actually. Okay. Anyhow, after providing all those forces, after fixing all those sizes, the moment when I'm going to run this design actually, it shows the efficiency factors, how much utilization ratio which has been governed actually. So with this, again, I can go back and optimize the weld thickness. I can go back and reduce the plate thickness and everything which I can do it. I mean, okay, I'll go with 8 millimeter thickness, the same grade S275. And can you see different kind of welds are there? One is you can do only one side weld, another one is other side weld, and third one is that shows both side weld. Usually in the base plate, I mean, you will do both side weld actually, the third one. Okay. So I'm going to click the third one. Okay. Yeah. So flange and the weld as web as well. Six. Okay. Yeah, fantastic. Okay. Then going with the foundation back, you need to understand one thing: IDEA Statica will never govern the foundation. So similar to the master series. Remember actually when we did the base plate connection in master series, I mean, even we did not model the foundation. We did not model the play, what you call the pedestal dimension as well. It does not govern. Huh? It will only govern there is a concrete and concrete grade. It will calculate the pull-out test with respect to the bond strength. I mean, okay. So don't bother about the size of foundation here too much. But you can just go with the grade of concrete. You can change the grade of concrete, and you know that as per authority, the concrete grade for the cubical strength, it should not be less than 40. So if it is 40, then cylindrical should be 32. It depends. I'll go for C40 50. I'm not going to change it as it is for time being. Okay. Okay. Then coming back to this coming back to the shear force transfer. Okay, friction, shear legs, and as well as anchor, which is only friction. Okay, which you are going to get it actually. Yeah, we'll change it to anchor because you do have, you are providing the anchor already, right? Okay, when you don't have anchor actually, then it's fine. I mean, okay, but that is not the case actually. Since we do have an anchor, so the shear force is going to be transferred through the anchor. And standoff, there is a three kind of methodology in terms of practicality. The practicality below the base plate, either you will go for grouting, which is a mortar joint, or you can leave the gap. Okay, or you can keep the direct. No one is going to do it, right? Actually, so below the base plate you will have minimum 25 to 30 millimeter of routing. I mean, okay, I'll go with the motor joint. I mean, okay. Then yeah, forget about what do you call the thickness of the foundation actually, because it does not govern, I told but anchor, make sure whatever the embedment length which you have been provided, actually the thickness supposed to be more than that. Okay, because the foundation thickness is already taken 600 millimeters. Okay, then thickness of the base plate. Yeah, here. So change it to 16 millimeters actually, since I'm using same. So I'm going to keep it same thickness. Okay, that's all. Okay. Okay. Now coming back to the forces. Coming back to the forces. Yeah, here. And can you just, I'm going to zoom in. Can you see? It shows the direction of the forces as well. Okay. What we have, so which is Fy 16 kilonewton. Okay. 16, 12, minus 17, 19, 20. Okay. So minus 16. Okay. Okay. I'm going back to the stat again. Stat again. Can you see here? Here Fy in IDEA Statica, it is referring to N. Here Fx and Fz in IDEA Statica is referring Vy and Vz actually. Okay. So here Fx is nothing but Vy. Here Fz is nothing but Vz actually. Okay. So going back to the Excel sheet again. So which is 16 minus 17. So here 16 minus 17. Okay. Again to the moment. Okay. So Mx and Mz, right? Yeah. Which is minus 19. My. Yeah. Fantastic. Yeah, open this Excel sheet. Yeah, Fy is 12 kilonewton. Yeah, the axial is 12 kilonewton. Okay. Can you see here? There is an option called calculate. Can you see here? Calculate. So the moment when I'm going to click the calculate, okay, calculate. Okay. Be with me. See, say for an example, it shows the efficiency factor here. Okay. So what is the efficiency factor? The plate is being only utilized like, what do you call 30 percentage, right? Okay. The anchor, it has been gone like, more than 100 percentage, which is like, three times higher than the, what do you call, the allowable tension force. Okay. The weld, it is a bottleneck, 98.1. Still, if you can increase like, 1 mm further, it will go away. And this is the bond strength, 54 percentage. Okay. So what I'm going to fix it actually, in fact, I need to only fix anchor. So even you don't need to like, touch the weld as well, because been used like, what do you call ultimate force. So you don't need to touch the weld. So what I'm going to do, I'll only change the anchor first. Okay. I'll only change the anchor. So the anchor diameters, what we have used, 16 actually. Okay. Okay. So first I will change it to anchor is 20. Let me see like 22. 22. Okay. Let me run the calculation. If not, I will add it like, extra bolt. Okay. So fantastic. See, the moment when I'm just, what do you call changing the anchor 20. So let me just, what do you call change it to 20 again. See, 84.5 percentage. Correct? Yeah. 84.5 percentage. And weld 98.1. If you want, you can leave it as it is. If not, you can just, what do you call, change the weld thickness from 8 to, yeah, 10. Yeah. And again, go back and run the calculation. It's fine, like, 97.3. Okay. Okay. So how to extract the report? So I'm done with this actually. I've been apply the forces. I have seen like, the short summary, what exactly we required in terms of analysis, checking the efficiency factor for the plate and anchors and weld, and even for like, the bond strength. I mean, so I need to extract the report. Can you see there is an option called report? The moment when you click the report, even either you can go for like, short summary report, or if you want, you can go for like, detailed report actually. Yeah, here. And drawings, because I need the drawings, the base plate dimension, everything in addition to this. And here, so these options actually, these options, I mean, these options, it all like, showing the detailed report completely. These are all options. The one which I'm going to click it now. Actually. Okay. These are all option. It shows the detailed report. Yeah. So I'm going to reference this. Takes some time, like, because when it is generating the detailed report, I mean, yeah. So coming down. Okay. So it shows again the summary here. Okay. Coming down. Okay. So this is the modeling, the one which you did, I mean. Okay. And this is the plate stress. Can you see here the plate stress? Okay, can you see the plate stress in a different colors actually? Okay, where exactly you need to, you do have like, the close to the 275 stresses, I mean. Okay, come down. And this is each anchor, like, how much utilization factor has been like, considered. Come down. Okay, these are all like, bit of and a kind of like, calculation which usually shows. In addition to this, it shows the diagram as well. I mean. So what is the base plate dimension? And what is the edge distance? Okay, and what is the bolt diameters? Okay, and what is the weld thickness? Yeah, so this is what it is. So hope it's clear, right? Is it my voice is clear? Okay,
Yes, sir.
fantastic. Okay, okay. There is any question in this? I mean, please ask me, or else I will go for like, further connections. Yeah, okay. Okay, let me go for like, further connections. I'll open the stat model again. Okay, so shift N. which is the node number. So shift n is been used to identify the node number. I'll go for shift N and shift B again. So shift B shows the beam number as well and node number as well. Okay. So let me, what do you call, going to design this connection again. Okay. So which is beam number 36, and I need to extract the beam forces at 15, right? Same command. I'm not going to change anything like, the commands in order to avoid the confusion. So there is a, what do you call, command called result setup. So in the ranges, instead of node, I will type the beam number, which is 36. But I need like, node number 15. The reason why I'm just, mentioning beam, because I need to extract the beam n forces summary. So in order to extract the beam forces, I need to enter the beam number. But obviously, like this beam, it has like, two nodes. Definitely it shows both the node, but only I will extract the reactions only for the beam 15. Okay. The loads as it is there for the ultimate factored load. Okay. Then I'll go for mode, post processing, beam, forces. See, can you see 36, 15 and 16, 15 and 16. Summary here. Okay. So I'll just copy and I'll paste it right here. Okay. Right here. Then looking at this, going back to the STAD model, the axial forces for the beam is Fx, correct? Fx. This is axial, which is going to be defined either tension or compression. And I could have like, horizontal shear in terms of FZ direction, vertical shear, which is Fy. Okay. And of course, obviously, I do have, which is indirect tension due to the moment as well. Okay. So let me check the beam 15, which is here. So the maximum is, which I'm going to get like, 3.13. Yeah, this is 16. Yeah, 3.13 actually. 3.13. Okay, fantastic. So I'll highlight this. Yeah. So what I'm going to get, this is the direct tension -4 and indirect tension, which is 3. Okay. So the axial, what you have, -4, right? And which is here, -4, right? Tension, right? Okay. Then Fy, which is 2, and Fz, which is 1, -1. Okay, you can leave it this because it's 0.13, you can put 0 as well. The Mx 0 again, mz 0.4 also consider 0. Again, it's 3.13, which is 4 kilometer. Fantastic. Okay. So you will have like, okay, the direct tension is -4 and 2. Okay. So let me open the IDEA Statica again. Okay. And there is an option called connection design. Again, I'll go back to the like, the same options. I'm not going to change it. Yeah. So now column to beam connection. Huh? Column to beam connection. Yeah. The second one. Can you see here? The second one, the one which I clicked here. Okay. Yeah. Coming back here, so it has a several option. So I don't want to confuse you. I will show you like, both, which has like, bolded and as well as like, what do you call welded connection as well. Okay. So I'm selecting like, bolded connection first. Okay. Okay. So let me change the section sizes first. Open the STAD model. I'm opening the STAD model. Okay. What is the beam size? So property, which is 178, 102, 19. Okay. I'll change it 178, 102, 19 first. 178, which is UB. Yeah, 102, 19. Okay. Okay. Yeah. Change the beam. Let me go to the, what do you call, the columns. Again, 203, 203, 46, right? Columns. Yeah. Columns. Back here. All. You see. 203, 203, 46. Okay. Okay. Yeah. Yeah. So I've changed, like, what do you call, section sizes. Okay. Let me go to the forces before changing the base plate. Okay. See the tension, which I'm getting like a -4, -4. Yeah. Can you see here? The moment when I put, like, -4, it shows like compression, right? Actually. So if I'm changing, like, positive, so you can easily identify whether you've been mentioned the compression force or tension force. For it automatically turn into direct tension actually. Okay. Now going back to the, what do you call, the Excel sheet again, which is Fy is 2 kilonewton. Okay. The Fy is 2 kilonewton, which is the vertical shear, right? Which is the vertical shear, and mz is 4 actually. Okay, fantastic. So the vertical shear, yeah, vz 2 kilonewton. So this is the vertical shear. Okay, and mz 4. Okay, fantastic. Oh, mz actually here it's not mz actually. Okay, put it in my. You can see even the direction. Can you see? You can see lively. Okay, so how this beam is going to be, like, fail under this moment. So it's a overturning moment. Okay, fantastic. Now going back to the plate. Okay, end plate. See, the moment when you select this plate, actually, it automatically shows in a different colors, actually. Okay, because whatever the colors it shows the same colors. Okay, okay. So what is the beam size? 178, right? Actually, yeah, yeah. Okay, fantastic. So the edge distance it shows 25 millimeters here. So what I'm going to do, I'll increase the edge distance by 40 millimeters. Okay, and here also from the web actually it is very close, right? So what I'm going to do, in order to tight this bolt, I'll keep it like, 40 millimeters or minimum 30 millimeters. So 30 plus 30 actually, which is 60. So in order, instead of 51, I'll change it to, what do you call, 60 millimeters, 60 millimeters. Okay. Then I'll keep the edge distance actually. Let me adjust them. Yeah. So instead of 101, it becomes like, 60. Yes. Even you can keep it 35 millimeters. Okay, 60 also is too close. So which is 70 millimeters. Okay. See, I'm keeping what do you call 35, 70, which is very close actually. So I try this, which is very close. Okay, because you need to count the web thickness as well. The web thickness will be 10 millimeters. Okay, so if it is 60, it will be very close. So what has been taken, what do you call, almost 101 millimeters actually. Okay, 101 millimeters. And keeping the edge distance, the 30. Here it is not a problem, okay, because the edge distance will have issue in the, mainly in the anchor bolt, so which is 40 to 50 millimeters, because there the pull out failure will be happening frequently. So here you don't have any issue. You can maintain minimum 1.25 times of diameter of the bolt. Okay. So our 30 to 40 millimeters actually you can keep it. Okay. So I'm just keeping 30 millimeters as it is. Yeah. Changing the plate thickness, 12 millimeter. Okay. Yeah. Yeah. Weld thickness, minimum 5 millimeters. Yeah. Run the calculation. Yeah. Can you see here the summary? Okay. The plates is not going to be take anything because the forces is very minor. Okay, and the bolt, which is 18.7 percentage, but still it shows the stresses. So when you go for the detailed report, it shows the stresses as well. So the bolt, which is 18.7 percentage, did I change the bolt diameters? Let me see the bolt diameters as well. Yeah, M20. So I'll go for M12. Well, that's fantastic. Rerun the calculation. I'm going to rerun the calculation. Yeah, still going with 12 millimeters, it is only 40 percentage, and weld is 33 percentage. I cannot go for less than what do you call 5 millimeter thickness as per authority requirements, 33 percentage. Okay, and going back to the analysis report, yeah, the same option I'm going to click it here. Yeah, so it will give you different view of the modeling. Okay, and of course coming back, and it shows the section sizes as well, section sizes, and it shows the summary as well. Okay, and going below, yeah, this is, I told you, no, so it doesn't show the plate stresses over there, but it shows in the detailed analysis report. Okay, the plate stresses is very less, that's the reason it doesn't show. It's only it's closer to 25 mp. Okay, 25 newton per millimeter square, and even here, which is very close to here actually, it is all less. See, I'm talking about only the plate, huh? Even the main member also will be under stress, but I don't bother about the main members. Only I'm going to we are here only designing the connections alone. Okay, and yeah, going with the bolt, each bolt, what is the utilization factors which has been taken. Okay, and going down, yeah, based on the weld thickness, actually, what is the utilization ratio? Yeah, so this is the drawing as well, actually. Okay, this is the drawing as well. So the edge distance is 30 to 40 millimeters. You can keep it. Yeah. Okay. So here you don't have any problem. Again, I'm telling actually. It's not what they call foundation. You do have pull-out failure. There you need to keep it minimum 40 to 50 millimeters. The reason why 50 millimeters you are keeping the anchor, I cannot keep it in the cover side actually, because the minimum cover which you're going to provide in the pedestal is 50 millimeters, right? So I need to provide the anchor inside the reinforcement actually. So there it has concerns in pedestal where you're going to place the edge distance, but here it doesn't matter actually. So minimum 30 to 40 millimeters is fine. Okay. Yeah. Anyone has questions, please do ask me, or else I'll go for next connection. The similar to this, I'll go for the bolded connections. Sorry, the welded connection. The similar, the one which you have seen is bolded connection. I'll go with the welded connections. Is it my voice is clear?
Yes, sir.
Okay. Shall we go with the welded connection, the similar one?
Sure, sir.
Okay, fantastic. Okay. The same connections, I'm going to change it. Okay, to okay, the same connections, I'm going to change it to what do you call welded connections. Okay, keeping the same forces. So what I'm going to do, see here, the beauty is what actually, when I'm just untick anything, I mean, it doesn't show the what do you call member. It's simply you're hiding the members actually. So okay, if I want to hide the beams, so it will hide actually. I getting your point. Okay, so the similar way, what I'm going to do actually, so I'll hide the base plate. Okay, because there won't be any kind of plate here, right? Actually, okay. Now going with the weld dummy, okay, here I'll right click. Yeah, I'll right click here, the operations. There's an option called new operations. Whatever you've been keep on adding, the plates or weld actually. These are all which comes under operation. Either you can select from here or you can select in the rightmost corner. There's a direct option is here, operations. Okay. So the easiest way you can just do it here as well. Right click and there is a new operations. Okay. It shows different. I don't want to confuse you showing all. Okay, and this one which I'm going to cut it actually the extra member which has been protruding. Okay, that's all. The moment when I did actually automatically it will cut, it will take it to the welded connection. Okay, so what I'm going to do, I'll change it to what do you call the weld 5 millimeters. Yeah, 5 millimeters actually. So that's all. Remind the forces, everything it remains same. I'm not going to do anything. So I'll directly go and do the calculation. Okay, fantastic. It doesn't have any kind of concerns of the bold at all because I've already removed the bold. So it will have only the concerns of what? Weld. I mean. So whatsoever the forces, the one which we have mentioned, I mean, so those forces, it has to be catered by the weld thickness. But you know something, when we have seen the manual calculation, I've already told you, the weld capacity is much more higher than the bolded capacity, right? I mean, because the moment when you go for the weld, actually, it has 70 percentage of the area of the weld multiplied by the weld grade. It is a huge capacity, okay, even going with 3 mm thick weld. But fortunately, due to the authority requirements, I have to go for minimum 5 millimeter thickness of the weld, actually. Okay. So is it clear, right, everyone? Yeah. Yeah. Is it my voice is clear, right?
Yes, sir.
Fantastic. Okay. I'll go back to the other connections. Say for an example here, let me just go to the beam to beam connection here. Beam to beam connection and beam to column connection as well. Okay. The similar way, let me just run the analysis. Okay. Then shift N, then shift B. Okay, fantastic. So shift B, so can you just see the beam number is 6 and the node number is 2, right? So going with the result setup, I'm not going to change the option. Huh? Just be with me. Huh? The same option. Just try to understand the concept. The moment when you understand the concept, I'm 100% sure you can deal with any kind of connection because the concept is more important than the numbers. What I believe, So the range, okay. Then the beam number is 6. Okay, I told you, right? Because when you want to extract the beam n forces summary, because only concentrating on the beam numbers. Okay, beam. Then the node is 2. Let me just check the. Okay, of course. I mean, we did not someone has did the ultimate combination in the class. But however, I'll take it all the cases. Huh? Okay. Then go to the mode post processing beam forces summary. Okay. What it is? Number 2, right? Okay. So I'll go in the Excel sheet. Yeah. Yeah. So which beam you're talking about here? More. So this beam you're talking about here, right? which is Fz, not Fx. We need to understand the axial forces is what? Fz actually. Okay. So the axial forces here, it gets changed here. Fz, which is the tension. So Fz is how much? So which I can say the node number is what? The node number is 2. Okay, the node number is 2. So node number 2. So am I getting like, Fz here? It is all 0. Direct tension, there won't be any kind of direct tension, but don't think that there won't be any kind of tension. I do have indirect tension. So which is 4.69, which is 5 kilonewton. So maximum, but this is node number 6. So node number 2, 4.5. Yeah, of course. So which is 5 kilonewton. Yeah, 5. Rest others is 0. Then I'll go for like, shear. Yeah, 5. And this is talking about like, 3. Yeah. And yeah, 3 here. And Fy, which is 9. Okay, fantastic. Okay, 9. Okay. So let me open the connection design again. So I'll just close this. I'll just close this. Okay. I'll go back to the. So I can change it the same connection, but I don't want to do that. Because the reason why actually, so let you can understand when you're opening the IDEA Statica, the whenever you want to go for like new connections. I mean, so that's the reason I'm just showing again and again, like going back to the options. Okay. So the same first one actually. Yeah. Beam to column. Ah. Yeah. Okay. So let's change the forces. Let's change the section sizes first, as usual actually. You see 254, 254, 73. 254, 254, 73. Column. Yeah. The beam, 457, 191, 74. 457, 191, 74. Okay, fantastic. Okay. So now let me go to the what do you call adjusting the base plate, the plate. Okay. So the plate dimension. So I'll just extend 20 millimeters, I mean, all around. Okay. Then I'll adjust the base plate, what do you call? So the edge distance. So edge distance will be like, the 40 millimeters from the section, actually 40 millimeters. Okay, from the section. Yeah, not from the top section, actually. Take it 60 because considering the flange thickness as well. Okay, fantastic. And this 20 millimeters. Yeah, this is from the section, actually. Let me just, adjust this. Yeah, okay. So keeping 230 millimeters and leaving, like, what do you call, 20 here. So let me say 30 millimeters, the edge distance. Yeah, 30 edge distance. Yeah, okay. I'm only keeping, like, two bolt, as it is. I'm removing the stiffener, the back stiffener. Okay. Then going with the weld. Yeah, changing the weld thickness to 5 millimeters, 5 mm. Okay. Now changing the forces, forces, and going back to the Excel sheet. So FZ0 direct tension is 0. So which is 935 FY 9 3 3 5. Right? Yeah. This is the forces. This is the forces. Yeah, that's all. And I'll just change the bolt diameters and plate thickness as well before running it. So the plate thickness is 12 millimeter and the bolt diameters is, yeah, I'll change it to 12 millimeter as well. Yeah. So I'll just run the analysis. The main thing is, what happened actually? The main thing is actually you need to understand the, what do you call, extracting the forces from the stat model. That is more important. So the main thing is what actually you need to understand the forces from the stat model. Okay. Okay. So now before it shows the errors, right? Actually, it shows the errors. You know what happened actually? There won't be any kind of connection with the the plate to the columns. Can you see here? The weld which has been, like, having from beam to base plate, but there won't be any kind of connections. So for that, so the moment when I say the weld which has been there already default, so automatically, like, the weld has been, like, connected to the plate. So, something like, how does is going to be happened, right? Inside. Okay, fantastic. So going to the calculate. Okay. Then bolt will be 4.5 percentage. Weld will be 12.4 percentage. Adding the bolt also, I will show you how to add the bolt. So can you see here? So we can easily adjust the dimension, okay, by adding the base plate here, actually, okay, by adding the additional bolt. So for an example, you can equalize the dimension as well. I can equalize the dimension actually. So 117, 110 actually. So I can make it like, three of 110, 117 plus 117 plus 110 divided by 3. So which is 112, right? Yeah. Plus. So I can make it like, equalize. Yeah. So is it clear, right? Yeah.
Yes.
Yeah. Fantastic. Okay. So going back to, I'll just show you beam to beam connections, the main connections here, like which is called like, the apex connections. The one which you have been seeing, technically it is called like, what do you call eaves connection. Then the one which I'm going to show you like, apex connection. Okay. The beam number is 6, but whereas the node number is, what do you call, 6. Yeah. Both are 6. Going back to like, the same forces. I do have the 6 here. I do have the 6 here. Okay. So which is Fz, again it's a tension. So Fz for 6, which I'm going to get 0 again. So Fy for 6, again it is 0. But Fx, I'll get it like, 6, which is 1.2. So which is 2 kilonewton. 2 Fy is 0. And Mz, I'm getting minus 17, which is minus 18. Okay. So shear vertical, yeah, this is lateral. Horizontal shear is 2, moment is minus 18. Yeah. So going back to the connection again. Yeah. So beam to beam connections. Yeah, just a second, Amina. I'll close it again. I'll open it. Yeah. I'll just open the IDEA StatiCa again. So under beam to beam. So this is with the haunch. This is without haunch. Okay. So without haunch, I'll go for it. Okay. Okay. I'll change the section sizes. So 457, 190, 174, UB, 190, 174. Yeah. The another section size also is same. So angle actually, like, what do you call? Let's, I'll go for here, which is 15-degree slope here, right? 15-degree. I mean. Okay. So I'll take it 15-degree. Another one also 15-degree. Yeah. Let me just, what do you call? They change the forces. The lateral shear, which is 2 kilonewton. And the moment is 19 kilonewton. Yeah. Okay. And having with the base plate, having with the base plate, the thickness I'll change it to like 12 millimeter, the minimum thickness. Okay. And this is what top. So in order to receive the weld thickness on top actually, so you'll have been projecting minimum 8 to 10 millimeters, because we'll have the weld on top of it actually. Okay. Okay. Then I'll just go for what do you call the bolt M12. Okay. Then I'm just adjusting the spacing of the bolt here. So let me just see. 60, 253, 60. Okay. So 60 plus 253, 60 divided by 3. 124. 124. I'm changing with the weld thickness 5 millimeter on both sides. That's all actually. And do the calculation. Yeah. So again, the plate it shows 0. It does not mean that actually the plate does not have any kind of stresses. When you go for detailed calculation, it shows the plate stresses as well. And the bolt, it has been governed only 44 percentage. The weld, which is 28.5 percentage. So I'll just show you the detailed calculation. Showing here what is the plate stress. Okay, and drawing as well. Okay. Okay. So this is the section sizes. This is the what do you call different views in the modeling. Okay. And this is the plate stresses, which is between less than 25 MPa. And there are some places actually which has been exceeding 25 to 50 MPa, whereas the plate stress is 275 MPa, the allowable. Okay, this is the utilization factor for the bolts. And these are the bit of manual calculation. And this is the throat thickness, which is the weld thickness utilization ratio. Going back, and this is the what do you call the drawings for uh, the connection design, which is a base plate and as well as the bolt. Yeah, that's all. Is it clear, right?
Yes, sir.
Fantastic.
Yes.
Okay. Okay. So I'll just go to the splice connection. Yeah. Let me just show the splice connections here for the columns and as well as beam to beam. Okay. So for the splice connection, there are two ways. I mean, one is actually, let me just, what do you call, double click this beam. I'll go to shear bending. Okay. So I can just, move the cursor in order to see the moment. Okay. With respect to the distance. Say for an example, where exactly I do have zero moment actually, which is almost the distance of 1.146, I'll get no moment, which is almost zero, right? Actually. Okay. Fantastic. Where I do have maximum moment, I mean, by having this 0.467, which is not the maximum. Okay, this is the maximum 0.6. Even at the center, actually, it is only 0.3. Okay, but this is only for one load case. Huh? Okay, then you can just go for with respect to the combination. But in fact, you don't need to go here actually by selecting each and every one. Okay, so what I'm going to do, so I'll just create it the splice connections. Okay. Now what happened where the splice we can provide actually? The splice is going to be given in terms of site constraints where in terms of logistic wise I cannot transport the beam. Say for an example, what is the beam length actually? 6 meters or 12 meters, right? So in terms of logistic wise actually I cannot transport the beams for somewhere in the site constraints. Then I can provide the splice connection 50 centi, 60 centi or up to 1 meters. And the remaining beam I can take it from the factory. I can do the bolted connections, right? Actually, of course, none of the consultant is going to be accept the welded connection at site, right? Actually, okay, fine. So another thing is, I mean, in order in terms of technicality, in terms of structural design wise, where I can provide the splice connections. I'll double click again. Okay. So going back to the shear and bending, okay, then bending Z. Let me go for like, what do you call the ultimate combinations. Okay. Okay. So which is 0.7, 2.13, okay, 3.54, where I'm getting like, okay. So I can see 3.54 is been maximum. Okay. Here. Fantastic. Okay. So here, so it's a 15 node, which is 1.97 is the moment. 16 node, here it's 3.54. Okay. Now moving back to the cursor, I want to provide actually at 1 meter distance exactly, which is 1.5. Okay. Now the question comes, I mean, if I provide the moment here, if I provided the what do you call splice connections here, exactly at 50 centi distance, what happened? Your moment is 1.8, but here you've been talking about like in terms of less forces, maybe if forces is very huge at 50 centi, actually might be it will go for like 10 or 15 or 20 or 30 actually. Okay, look at the number, huh? Look at, try to understand the concept. So I'll just go for another 50 centi. What happened? My forces has reduced another 20-30%. The advantage what you're going to get it, I mean, in order to extend of 1 meter beam by welding from the factory, you're going to reduce the moment by 30% further. By reduction the 30% further, which you're going to optimize your plate thickness, which you're going to optimize the bolt diameter as well. You're trying to understand, right? Trying to get my point. Huh? Because instead of giving 50 centi of these place connections, I'll try to move another 50 centi, which is 1 meter actually, to reduce my moment in terms of 20 to 30 percentage. You're getting a point, 20 to 30 percentage. So what I'm going to do, okay, so can you just keep, I'm keeping the cursor, it's showing the three colors. So always the green which it shows is a starting point actually. Okay, so I'll just, right click here, insert nodes, 1 meters, add new point. Okay, okay, fantastic. So I've added a point 28 actually. Okay, so the beam number is 54, 28. So I'll just analyze it. Okay. Going back to the result setup, ranges, beam number 54. Either you can go for 36 as well, no problem. Okay. If you go for 36, it shows two numbers, 15 and 28. If you go for 54, it shows two numbers, 28 and 16. Huh? Okay. Check it like, what do you call ultimate combinations. Okay. Then mode, post processing. I need 28. Huh? Beam forces. Somewhere. Okay. So 28. So I'm going to like, what do you call, copy this again to the Excel sheet. I've done I'm going to do the splice connection here, okay, which is FX. FX is the actual, which is the tension. So let me go here. So FX, what is the node number? 28. So node number is 28. FX here almost 4.4, which is 5 kilonewton. Okay, so sorry here. 5 kilonewton, which is tension. What else? I do have FY, which is 28, 1.2, 1.3, so which is 2 kilonewton, and FZ0, MX0, MY, it's also MZ, which you're getting 1.6. Yeah, 3.5 is node number 16, and 18, yeah. So you'll have like, 1.6, which is 2 kilonewton. Okay, fantastic. 2. Okay. So now direct tension is 5, indirect tension, you will get it 2. Okay. So let me open the connection design again. Okay, connection design. Yeah. So I'm going like, beam to beam actually. This is the end plate, the one which you have seen now. So right below, so this is the splice connections. So create project. Okay. So change the section sizes first, I mean, as a routine, what we used to do. So what is the section sizes here? 178, 102, 90. 178, 102, 90. UB. Fantastic. And going back to the, what do you call, other side, it's the same size. Yeah. Going back to the, what do you call, forces. Yeah. So direct tension is 5. Okay. Direct tension is 5. And what do you call, the Fy is the vertical shear and moment. That's all. So the vertical shear is 2, 2, then 2. That's all. Okay. Now coming back to the, what do you call, plate thickness. Coming back to the plate thickness, change it to 12 millimeter plate thickness. Okay. Okay. Now coming back to the web plate, I'll remove this plate actually for an easy reference because it is more difficult while you're providing in the site. Okay. And the bottom plate actually. So can you see here? There are two plates is there. There are top plate and bottom plate. Let's adjust the bolts of later actually. I'll just remove the plate first time. So I do have plate on top. I'm going to remove the plate at the bottom. Okay, so can you see here? There is an option called backing plate. The moment when I click the backing plate, it shows here actually. Okay, it shows. I'll show in a different view for a more clarity. So when I'm just untick, automatically it goes here. Okay. Again, the similar way for the backing plate at the bottom as well. Yeah, fantastic. Okay. Now going with the bolt diameters of 12 millimeter. Okay. Now let's adjust the bolt. Okay. So 12, if you are keeping like, so 101 minus 60, the balance is actually 41. Okay. Then 1.25 times of 12 millimeter dia, how much you're getting? So 1.25 times of 12, yeah, 15 millimeters. So it's exactly same. Okay. So 10 minus 60, which is like, 41, right? So 41 divided by 2, which is 20. We do have only to 15 millimeters. So 5 millimeters more. Okay. And going below here, so same 30, 30. Yeah. And changing the bolt is M12. So having this side 2 bolt, having another side 2 bolt. That's all. So I'll rerun the analysis again. Okay. Can you see here? Yeah. Again, it shows 0, but it does not mean it is a 0. There is a stresses as well. And the bolt, which is only 10.9 percentage. So I'll go to the detailed report. Okay. And coming down, section sizes, different views from the models. Yeah, and what do you call? And this is the plate stresses. But of course, I mean, I'll show you in the graphical plate stresses, which is obviously like which is between 25 to 50. It's the maximum stress. The allowable is 275. And coming back to the bolts, so these are the utilization factor for the bolt. And coming back to what do you call? Yeah, yeah. This is the bolt diameters. Yeah, and this is the what do you call? The sketch which shows for the plate and the hole diameters and the edge distance and the plate dimension as well. So hope it's clear, right? Is it my voice is clear, right? Yeah.
Yes, sir.
Okay, fantastic. Okay. Now going back to again, like I'll go to the column splice connections. Okay. Okay. First, I'll go to the stat model. Stat model. The similar way, what I'm going to do. So I'll just check the shear bending. Okay. Going with the ultimate cases. Just to scroll down. Just to see, like which is maximum. So 9.32, I'm getting like 103 cases. Yeah. 9.85 as well, 104. Yeah, fantastic. 19.53, which is 109 as well. Okay. 19.53. Okay. Okay. Yeah, 19.53. Okay. Now what I'm going to do, okay. So either I can provide the best portion to provide the splice connections here. There won't be any kind of moment. Okay, here. So the moment is what? Almost zero. Okay, at 1.8 meter distance actually. It is not exactly half. It is, you can say, like more than one third actually, which you can say. But still, if you want to play in a safer side, if I can give you like what do you call, still at 1.25 meter also, which you are getting like less moment, which is 4.17 kilonewton meter actually. Okay. So now going with this, what I'm going to do, I'll create like 1.2 meters. Okay. Okay. Let me check again. 15 nodes, 23. 15 nodes, 23. Yeah. 15 nodes, 23. Where exactly you're getting from here? Huh? I'm going to what do you call create the splice connection from this point. Huh? Look at this. This is 15 actually. Yeah, okay. And this is one. Okay. Okay. So which is 1.2 meters only, right? 1.2 meters. You're getting 4.53. Okay. 4.53. Okay. Right click, insert to 1.2 meters, add new points. Okay. So what is the node number? 29 is the node number. Yeah. 29 is the node number. And the beam number, either you can take it 55, either you can take it 33H. Okay. So what I'm going to do now, for a cell setup, ranges, the beam number, I'm going to take it 55. Okay. Then loads, all ultimate cases. Okay. And 29, right? Mode. Yeah. Analyze. Mode, post processing, beam, forces, summary. Yeah, 55 and 29, right? Yeah, let me just, yeah, yeah, here. Okay, okay. I'm going back here again. The direct tension is what actually, which is Fy. So Fy here, Which node number you're talking about? 29. So the 29 node number Fy is almost you can say 9.13, 9.5 also is there. So 9.5, yeah, which is almost 10 kilonewton. 10 kilonewton. Okay. Then Fx, it's a 12.12, which is 13. Yeah, fantastic. Yeah. Where exactly you do have 10 kilonewton? Yeah, Fy. Let's go here from the moment actually. Okay. I don't want to confuse you. 4.58, 4.667, right? Okay. So Fy here 10 kilonewton and Fx here 11, Fz here minus 11, Mx 0, okay, My 3, Mz minus 5. Okay. Minus 5. So I'll just open the what do you call the connection design. Okay, same connections, same connections. So what I can do, I can only just flip it into 90 degree. Okay, I'm going to flip it into 90 degree actually. Okay, so let me. So how can we flip it actually? Just going back to the section sizes B1. Can you see here? There is a Y pitch degree actually. So the moment when I'm going to put 90 degree, it automatically flipped. This is first section, right? The second section also I'm going to flip it to minus 90, just bottom. Yeah, it's fantastic. Okay. Yeah, yeah. Now change it to the section sizes. Okay, what are the section sizes here? So 203, 203, 46. Okay, change it to 203, 203, 46 kg per meter. You see, 46. Again, down member, 46 kg per meter. Fantastic. And now going back to the forces. Okay, the direct tension. So what you're getting is minus 10 kilonewton, which is 10 kilonewton. Yeah. So here, so the direct tension is 10 kilonewton. Can you see here? And okay, the shear, I'll open the Excel sheet again just for your reference. So here, can you see minus 10 kilonewton? Okay, so there I told you, which is axial in terms of it is N. It shows the notation is N. So forget about the sign because you will get directly in the signs actually. It shows direct tension actually. Okay. Then going back to shear, the lateral is Fx 11 and both are 11. Both are 11, 11 actually. 11 minus 11. So I'll go back here. Okay. Then 11, sorry, 11, 11 minus 11. Okay. Now, coming back to the moment, okay, the mx is 3, no, my is 3, and mz is minus 5. Okay. Clear, right? So this is the minor axis moment. This is the major axis moment. Okay. Now going with the plate thickness. Okay. Going with the plate thickness. So 12 millimeter plate thickness. Okay, is 275. Make sure. And coming back to the bolt. So M12, which is grade 8.8. Fantastic. Okay. Then again, going with another sides, make sure 12 millimeter is 275 M12. Now let me adjust the, what do you call, let me adjust the bold spacing. Okay. So the edge distance which I'm going to give you, say which is 1.25 times of diameter of the bolt. So 12, which is 15. So I'll go for like, minimum 30 millimeters. So the plate thickness is 204. So 30 minus 30, edge distance 60, which is 144. Okay, so 144 divided by 2, which is 72. So 72, 72. Yeah. Okay. Then going here, okay, from half of the bolt, 60 plus 60, okay, the total plate dimension is 300 millimeters. Okay, 300 millimeters. I can make it like in a equalize actually. If not, I mean, leave it because this is half of the plate. You do have two bolt. Half of the plate, you do have two bolt here actually. Okay. Then, okay. Yeah, I'll go on other side. 72, 72. Yeah. So run the calculation. Can you see here? The bolt is only 51.4 percentage. So going back to the detailed report. Yeah. So these are the section sizes. This is the different view of modeling. Okay. And coming to the bolt diameters. So what exactly you entered, it shows everything. Huh? And these are the summary of the result. And coming back to the stresses, the plate stresses, which is like, between 25 to 50 MPa. And this is the bolt utilization ratio. And coming back to the, this is the drawings which shows, illustrate the drawings, both the cases, the plate dimension and the bolt distance as well. Actually. Yeah. Okay. Is that clear, right? Is it my voice is clear?
Yes,
Hello?
sir.
Yeah,
Yes,
it's
sir.
clear,
It's
right?
clear.
Okay, fantastic. See, what I'm trying to say actually, there are two soft tools. I mean, we already discussed about the master series. I'm not here to like, the shows the difference in soft tools. I mean, like, this one is good, this one is not good actually. Whichever is easy for you, you can take it. But one thing I can tell you, the master series has been like, I'm not going to promote, but it shows more in a realistic of like, an easy methodology of manual calculation which you can easily identify where is the problem, what it is actually. But if you can look at this kind of like, manual calculation, okay, yeah, yeah. See, I wouldn't say it has not been confusing, but I can say only thing is actually it has not been comparable with the master series because master series the manual calculation actually as such been like been in an easy way which you've been dealing with the kind of like simple calculation. It's also same, but every software has a limitation, so you need to understand first. Okay. So again, whichever is easy for you, you can take it. I'm not going to tell you again it is this is good and this is not good actually. But only thing is you need to understand about the constraints and limitation actually. Whichever you want to use it. No worries. Yeah. Is that clear, right? And both are acceptable in DM actually. Okay. Even in the master series also it has been acceptable by the authorities, not only DM authorities actually. And idea static also it has been accepted by the authorities actually. The more fond of idea static of people can lively see some kind of the images which shows the stress diagram, okay, and the utilization factors for the bold each and everything. So those things you will get it in the master series as well actually. Okay, the stress which you won't get it in terms of presentable, but you will get it the plate stresses over there in master series in a different format actually. But overall, that is different scenario and this is different scenario actually. Okay, so hope you can understand, right? Yeah. So is it clear, right? Is it my voice is clear? Yeah. Is it clear? Okay. Thank you so much, actually. Okay, the session is being recorded, so we will send you what do you call the recorded video as usual. The people are used to upload in the YouTubes. We'll ask them to upload as soon as possible. Yeah. Thank you so much. Yeah. Thanks a lot.
Thank you, sir.
Thank you so much. Thanks.